Hello, welcome to the short tutorial series of the Biomedical Engineering Department of Texas A&M University. Short tutorials is a collection of lectures that is not substituting your formal course, is only giving some complements, is giving you a chance to think, to see some more examples. It's more like supplement some materials for you to be able to understand even better what you already thought you understand, or get a few hints that tell you the importance that you could not get when you're doing the regular course. So we are putting together this short tutorial series in many topics. And the topic of today is differential equations. You know, differential equations are very important. All the engineering students, independent of being biomedical or not, they have to learn, they have to know how, why about the differential equations. So we're putting together a few of those video lectures that together makes the short tutorial series for the differential equations. So I hope you can enjoy, and that can help you in your topics related to differential equation. Differential equations are everywhere, as I said, and is very important for engineering. You know, I believe that we could not do what we do in engineering if we didn't have the relation between quantities and their variation, their relative variation. Can you imagine how can we understand biomedical processes if we don't have their understanding how things vary with temperature, for instance? You know, we make many sensors, we make many different imaging type of devices, we study fundamental process. Now, in biomedical engineering, we try to input all what we know in physics, chemistry, even mathematics to model, to come with new processing of the biological matter, and all that. Normally, we have quantities that needs to be understood, that needs to be able, that we need to be able to know how they vary. And vary with respect to what? Well, sometimes with respect to the time, sometimes with respect to other variable, other quantity, like temperature. You know, how the division of cells take place depending on the temperature of the organism. Oh, that's one of the things that we could model with differential equations. So differential equations basically are relating variation of quantities with other quantities and put in a mathematical expression. And that gives us the opportunity to contemplate many things that are influencing an individual process. And then we can more or less guess what's going to be, or we can extract from there effects that are important. So creating equations is important. If we're going to define differential equations, it's hard, but you know, if you ask your friend what is a differential equation, probably they're gonna say, well, is that equation that I have to solve to know the answer? But that's not really so complete, right? A differential equation is a mathematical expression, and if we ask the mathematicians, they're gonna say, well, this is a real mathematical expression imposing some conditions, and we ask if it is possible for such a quantity to have that dependence in those conditions. Then they express as a mathematical relation that ends by having a differential equation. So the mathematical point of view, that is a mathematical expression, a mathematical identity that can or cannot have solution. Sometimes we express, we believe that something is that way, but the mathematics tell us that's impossible. So it means that we are not right. If you are observing, like in engineering, some phenomena, and we write an expression, and the mathematics tell us that there is no solution for such expression, means that we are not having the right interpretation of the phenomena that we want to express mathematically. So, but for the mathematicians, that is a pure mathematical relation, and by knowing some principles of mathematics, they try to come with, first of all, if there's a solution, and second, how can I reach that solution, right? So on the mathematical point of view, it's more fundamental, I think. It's more like, this is a truth expression, and I have to understand if it is possible for such expression, for such conditions that link variation of one function with its dependent variable or so on, is possible. Now, if we ask engineering, what is a differential equation, he's going to give you a different answer. He's going to say, well, a differential equation is a mathematical expression that is somehow modeling, is somehow putting together what is going on between different quantities during an individual process or in an individual system, right? So there are many, many examples that we could give. For instance, for us in biomedical, it's always important to know how is the system behavior, so I can detect or I can interfere. I can produce, techniques for treating disease, right? And to know that is always important to understand how the whole system gets together to one different variable. I'm going to give you an example. When you are sick, when you have an infection, you drink antibiotics. And then you hope that antibiotics will be able to reach a special focus, a special target place. Well, to reach that special target place, when you drink antibiotic, there are many, many things that are necessary. So if I am interested to know how many molecules of these antibiotics really reach that infection site, that infection position, well, that's depending the capability of what I have put in my mouth to propagate, to be transported until that point. So there are many, many facts. The molecules has to percolate by membrane. Well, it has to be dissolved by your liquids. All that takes time, right? When you drink a pill, it doesn't dissolve immediately. It has time to be dissolved. And then once it's dissolved, it has to be in the right place to be absorbed by other things. And then has to go to the bloodstream, and then has to reach the interstitials of the cell, and then has to reach the cell, or has to be delivered in a situation where nearby microorganisms will be able to absorb. And the microorganism has to be able to absorb, and it doesn't do immediately. It takes time. So if I wanted to express how long it takes for antibiotic molecules to accumulate in some infection, you see, I'm going to have a differential equation. I'm going to have that the variation of the number of molecules in that special position depends on the solution of what I have taken. Depends on the capacity of transport of those molecules in many, many different parts. Depends on the elimination. Sometimes I take a drug, immediately is eliminated, never reaches the position. So you see, there are many, many facts that has to be put together, and that will determine how is the concentration of molecules of antibiotics in a specific position. How you do that? You do by putting together a differential equation that takes everything that I said to you that are important in this expression. So for us, a differential equation is a way to express mathematically a variation of quantities that we are interested, and that's depending of many things. Depends on many different issues, and then we put together. If we find out that there is no solution, so either that is impossible, so we're never going to make this antibiotic to reach that situation, or we are wrong in your model. We forgot to take in account in your expression something. So you see, being able to deal with differential equations is fundamental, especially in biomedical, because we deal with things that are varying all the time, and that's depending on many circumstances, depending on many other things. And that's why we have to learn differential equations. We learn differential equations to be able to visualize, to be able to have under control many processes that are important. When I consider one term in this big equation, and I see that the solution that I found in the laboratory is equivalent, I say, oh, I took in account all the important facts related to this phenomenon. So there is no question that differential equations are important. And it is a complicated topic in the sense that we have to know many bases of mathematics to be able to deal with the differential equation. That's why we first learn calculus, and then we learn series, how express functions in series, and then we learn a little bit of transformations of functions, and then we learn how to deal with the differential equations. Okay, now let's give some examples of like simple phenomena that end by being differential equations. Thermal expansion. Nobody questioned that thermal expansion is a fundamental thing. The size of objects depend a lot on the temperature and the variation of temperature. And then there is a relation between the variation of temperature with the variation of the size of objects. This is called thermal expansion. And when we deal with thermal expansion, we know that something will grow if more atoms are there able to split apart, to increase the distance between them. So more matter that I have, more expansion I may end by when I vary the temperature. So it's not easy to relate those things and then say that the variation of a volume of a body will depend of the variation of the temperature. And will also depend on the initial or the beginning of the size of the volume of the matter that I'm considering. So normally we say that the relative variation depends on the temperature, and this is characterized by a coefficient. And this coefficient ends by being a coefficient that sometimes characterizes what type of metal, what type of matter I'm using. If you are using an implant, for instance, we do that a lot in biomedical, right? We have to know how small variation of temperature will be accommodating this. If you make things too tight or too loose, that will not accommodate normal variations of temperature that we may have in your body, right? Then we have to take that in account. So this is a true statement. So I start making a true statement that the relative variation must be proportional to the temperature. Which means this will be bigger if this is big. This will be smaller if this is smaller for the same variation of temperature, right? So this is what we take a concept from physics and we put together in expression. Now, when I deal with tiny variation of volumes and tiny variations of temperature, so the deltas may be differential quantities. Instead of delta, maybe dV. Instead of delta t, will be dt. So if I put the dt here and I put back here, this is what we call the variation of volume with temperature, or the derivative of volume with temperature. And that must be proportional to the original volume. And this constant is a constant that in a first approach, we say that this constant is independent of temperature. It's a constant. But normally that's not true. It will be temperature dependent, right? And then we have to, if we want to know how is the evolution of the size of an object like the implant as the temperature change, we should know the volume, we should know the material, which is related to this coefficient, and then we can find out. We can, even if the coefficient is dependent of temperature, this will be an equation. And any variation of volume with temperature is related to this. The instanted volume, because we made this so small that the volume is the instanted volume for that moment. And then we can create an equation. You see, the differential equation here is relating variation of volume and variation of temperature in an arbitrary situation. As I said, I put a coefficient here, but this could be a function of temperature. And it is an equation that will predict it to us how volume varies with temperature change. This is an example. Another example that we are very much familiar is variation of velocity. Everybody knows from mechanics the variation of velocity of anything depends on how is the strength of the mechanical efforts pushing that and how heavy is the mass, the inertia, and for how long I act this mechanical efforts, this mechanical force on that object. So normally the variation of velocity has to be proportional to the time that I act, but has to be proportional also to the mechanical force, to my efforts in that system. And of course has to be inversely proportional to the mass, because if the system is very heavy, oh boy, it will take much longer to speed up the object, or will take a mechanical effort much bigger to do that. Those are the facts, right? So I construct a relation between variation of velocity when I have time included. And of course, when I go to the tiny variation of time, that will mean a tiny variation, a differential variation of velocity by having an equation. This equation relates the rate of variation of velocity with the time, that normally we call acceleration, with the mechanical efforts that are made, which it can be dependent on time. There is no problem. This can be a complicated thing. A force that starts very strong and then comes down, or a force that starts very weak and then grow up in amplitude. Anything can be here. But you see, I end by having an equation that establishes the condition that allow me to now visualize, and in any situation, I can see how will be the variation of velocity depending on the external parameter, in this case force, the intrinsic parameter, which is the mass, and the time variation, which is something that's going on in my experiment all the time. Suppose I add the viscosity in this. I'm trying to speed up things, like the blood in the veins, and I need force, I need pressure for that. The heart is giving this pressure. I'm able to put together an expression. But now I know that some energy, some of my speed is being consumed by another phenomenon, by viscosity. So I have to take into account. I try to speed. If I didn't have this term, I will be back to my original relation. But I have something taking velocity. So my force is used to speed up but part of this is being removed. So everything I do has to be divided in increasing the velocity or removing the velocity by viscosity. And normally, you know, we can come with expressions. Normally are also differential equations to show to us how is the viscosity acting on velocity. Here I choose a model that's proportional to the velocity. So this is an expression, you know. If I have my body flowing, the velocity of flow may very well vary in time, and will vary in time depending on the velocity, but depending on the force, on the pressure, but also depending on the capability of losing velocity in the process by a force that we call viscous force, right? And this is a differential equation. This may be dependent on time too. You know, the blood is a very interesting viscous fluid. His viscosity is very complex for many, many reasons. It's not a single value, depends on many, many, many parameters. The oxygenation, the concentration of red cells, the concentration of white cells, and many other concentrations. The plasma itself, if you are sick, if you are filled with microorganisms in the blood, it may affect the flow. So you see, I could build up an equation with all those elements and then see what are the ones that are important for the flow of blood depending on all this. So those, of course, are examples. I'm trying to bring the examples to our field of biomedical engineering, but you see that I ended with an equation, and an equation that relates quantities with the variation of quantities, and that's called differential equation, because involves those derivatives, involve those rates of variation of quantities with respect to other quantities, like timing here, but could be other things, that like could be the concentration of oxygen. I may build up a full equation like this, only based on oxygenation of the blood, and try to find out how the things are affected. Okay, so you've seen that it's important. Even with simple examples that we had before, we can create those wonderful equations that allow us to visualize many effects in that phenomena, in that specific case, right? Okay, well, differential equations, we are now able to define in a little better way, and we could say that differential equations are mathematical expressions that allow us to understand systems of different natures and their interdependence, right? The interdependence of the phenomena with respect to the many possible quantities involved. So that will be a fair definition of differential equation, I think, for engineers like us. We could, and for physicists as well. In physics, we live the same problem. We want to relate variation and quantities in a system, and sometimes we have too many to deal with, right? And we needed to be able to put them together in equations, their interdependence, their variations, how one varies when the other varies and everything. And this is what we do creating the differential equations. Well, there are many laws, almost all, in nature, and we have to, you know, the basic science like physics, like chemistry, they normally help us to understand the better fundamental laws of nature. So there are a couple of fundamental laws, you know, it's not infinite, not that we know. And based on those laws, we try to build up understanding of the phenomena. You know, when we learn some law, like Newton's mechanical law, we don't apply only for a tiny object being accelerate on the street. We apply for body. We apply for resistance of bones. We apply for everything, because that's a law. And a law applies for everybody, for all the systems. So normally, many laws of nature are expressed through differential equations. This is a very important fact. I want to highlight this. Many laws of nature are expressed through differential equation. This is a very fundamental thing that by itself justify why we need to learn differential equations. Because we're going to deal with laws that are present on nature. The way that nature presents itself, the way that everything obeys those laws are important for us to visualize and to come with new devices, to come with new procedures for testing things. We have to understand the fundamental laws, right? So once we understand the fundamental laws, we needed to put them together in our specific problem. And because many of the laws in nature are expressed in terms of differential equation, means that to model, to understand our own system, we'll be able to do if we know how to put together differential equations. And of course, we need to know how to solve the differential equations as well. But, sometimes we neglect the first part. We believe that a course in differential equation should only teach us how to solve, but we have to learn how to construct. Because, we're going to construct the basis on the basis of fundamental principles. That's why you need to know very well the fundamental principles so you can build up nice differential equations that represent the system you want to understand, or the new device you want to do. You want to do a new device for controlling blood pressure. It's better to know very well how to use principles to measure variations of pressure, to be able to do feedback and to things like this. And that will mostly be expressed by differential equations. So this is important. And all the engineers should know that what we do in constructing differential equations is putting together basic principles that we learn in many courses, basic courses. That's why it's important to learn basic physics, to learn basic mathematics, to learn basic chemistry, to learn basics everything, because we need to be able to put together. Engineering is this. Is putting together basic knowledge to apply to something. And we need to do that. And to do that, we need to know things. So don't think that you are spoiling your time by looking at physics lecture or by looking at chemistry lectures. Oh, why am I want to know that? I want to construct machines to help life. But to do that, you need to know the base concepts. And most probably you needed to know how to put them together. And to put them together, you needed the differential equations. Okay, here I put another example that's very common for engineering, which is chemical reactions. We all know what's a chemical reaction. You put the reactants together, they will produce some other stuff. But there is a chance that this other stuff dismissed by itself and coming back to the original reactants. This is what we call equilibrium, or not necessarily you need to be in equilibrium, but it's a possibility. If those arrows will be equal, will be an equilibrium, but it's not. Here I'm saying that A plus B is forming more C than C is forming A plus B. And you want to understand, you want to mix those things, and then you want to say, well, and now how long I have to wait to have the decent concentration of C, for instance. So how you do that? Well, we all know that reactions happens at the intermolecular level. Molecules has to get together, to have chemical reaction, to exchange electron, to exchange mass, to change the configuration of chemical bonds and everything. And by the way, chemical reactions will be another topic of short tutorial in this short tutorial series in the coming future. But you know, you have an equation here. You have this is an expression of what you're observing, right? A simple. And then you have to put mathematics on the top of that. And you know that how many molecules of this is forming depending on each of those. And I need one of those to make one of those. So it's natural that the rate of formation of this guy will depending on the one of these plus one of these. So the concentration of C depends on the concentration of the product. Because if one then goes to zero, the reaction is stopped. So if I want to know what is the time variation of this concentration, I have to know that it must depend on this. But as I told you, there is also something consuming this. So there is some process that is decreasing the concentration of this guy with the time, which is the inverse process. Is this guy that depends on itself, probably depend on temperature, depend on many things, producing A plus B. So there is a negative sign here saying that, well, this part of the arrow corresponded to negative. This part of the arrow adds C to my container, to my system. This part of the arrow subtract C from my system. And if I know this, that this subtract and that adds, I'm able to put this equation together. Those are normally called constant of reaction or rate constant of the equations. This is giving something that tells us what, when A and B gets together, what's the probability, what's a chance to make. If this is big, it's a big chance that they will produce C. If this is small, it's a small chance. Normally knowing those constants is what let me design a reactor, is what let me predict the rate of formation of molecules in a reaction. Now, but maybe I'm interested to know how is the variation of A. I'm consuming A, so I want to know how much A is consuming, because sometimes I want to put together a process that I'm feeding molecules to be able to go on continuously. So the variation of A, now I am in this side of the equation. The variation of A with time, which is the time derivative of the concentration, will have a positive for this arrow. So depending on the concentration of C, I may increase the concentration of A because of this process, because of this K2. But the reaction will consume. So the reaction taking place, the presence of B here, together with A, will consume the A molecule. So this happens. And of course, I may want now an equation for B, I may, and so on. You know that you learn in basic chemistry, if we had a 2 here, you know, if you have a 2 here, you know that this will come square, right? This will come square because I need 2 molecules of this to match with 1B to give 1C. We all learned this in basic chemistry. And this is what? What is this? Differential equation. Differential equation to be able to mathematically express a chemical reaction taking place. And if you think that chemical reactions are not important for biomedical, you are in the wrong place, because they are very important. Everything we do is related to type of chemical reaction. Sometimes transference of charge, sometimes transference of energy, many transport phenomena that can be expressed that way. So you see, chemical is important, chemical reactions, and they are intimately connected to differential equation. So to understand those process, well, we needed to know that how the differential equations takes place. Okay, well, now that you understand well the differential equations, we certainly can start to build up important questions related to the construction and to the solution of the differential equation. In the next lecture of this short tutorial, I'm going to start to explain to you how to solve the equations. And I'm going to start to explain to you what kind of methods we need to use to solve the equations. But I will never give up that knowing how to construct an equation is as important as how to solve the equation. See you in the next lecture.